Hello again, it's James. This is problem 7 from homework 7. It's about the force per meter on a lightning bolt at the equator. And the reason we're talking about the lightning bolt being at the equator is because at the equator, the Earth's magnetic field is parallel to the ground, roughly. And so something going straight down or straight up is subject to the maximum magnetic force if the thing is a current. Okay. All right, so number 7 says, what's the force per meter on a lightning bolt at the equator that carries 20,000 amps perpendicular to the Earth's 3 times 10 to the negative 5 Tesla field? Well, it's a current, so we know that the force on the current is IL cross B. And it's not a current in a wire, but it's still a current. So this equation still applies. And the magnitude is ILB sine theta, where theta is the angle between the first vector and the second, as is always the case with the magnitude of a cross product. Okay, and so we're calculating the force. All we have to do, we're calculating the force per meter. So I'm going to divide by L on both sides and call it the force divided by L, where I'll say that L is a meter in the end. And better than that, I'll say I'm trying to calculate the force per unit length. And automatically, the force per unit length in MKS units or SI units will be the force per meter. So what I want to do is divide by L on both sides, which gives me IB sine theta. And the current is 20,000 amps. B is the 3 times 10 to the negative 5 Tesla. And it's the problem says that the current is perpendicular to the field, so theta is 90 degrees, or sine theta is just 1. Sine of 90 is 1. And so you wind up with 6 times 10 to the negative 1, or 0.6 Newton per meter. Right. Oh, and I suppose the way the problem is worded, it says the force per meter. Yeah, that's fine. It's the force per meter. It's also the force per unit length in MKS units. All right, and then so part B, that's part A. Part B says, what's the direction of the force if the current is straight up and the Earth's field direction is due north, parallel to the ground? Okay, so the current is up, so that's IL, and we'll say that this direction is north. That's the direction of the B field. And so we do our right-hand rule. Remember, the cross product we're talking about is IL cross B. So I put my fingers of my right hand along the first vector, which is IL in IL cross B. And I slap the second vector with my palm, which I can do only if my thumb points into the page. So the direction of the force is into the page. And I'm going to talk about what compass direction that is in a second. But remember, the other way to think about the right-hand rule, I can say to myself, well, the force, which is the cross product, has to be perpendicular to both of the vectors, IL and B. And so IL and B are in the plane of the page. So the force has to be either up out of the page or down into the page. If the force is up out of the page and I put my fingers along IL, then I can't slap B with my palm easily, right? I can slap it easily with the backs of my fingers, or I can go all the way around, twist my wrist, and yeah, it's not easy. So my thumb up out of the page is wrong. My thumb should be down of my right hand. My thumb should be down into the page. I put my fingers along IL, the first vector in IL cross B, and I can easily slap B, the second vector. And so the cross product, which is the force, points in the direction of my thumb, which is into the page when I can perform the slapping motion easily. Okay, so the force is into the page if north is to the right of the page and up is to the top of the page. But what direction on the compass is that? Well, I think about facing north and turning left, right? Because if I face north and I turn my head left, then I will be looking in the direction of the force. So just picture yourself facing north and turning left, which is the same as facing the right side of the page and turning toward into the page. So if I'm facing north and I turn to my left, I am then looking to the west. And so this is west. Okay, so that's the answer, 0.6 Newton per meter west. Hope that this has been useful, and thank you for listening. Have a nice day.